So today me, Vinayak, Devang and Samyog will be presenting our project Simplified Robot-Aided Electric Vehicle Routing with Lockers and Prime Customers. This project explores how hybrid last-mile delivery systems using EVs, robots and lockers can reduce routing cost and improve customer coverage. This work is based on a research-level routing problem, but our goal was to make it tractable and implementable using the concepts from our course Routing and Scheduling. Modern last mile delivery no longer relies on trucks and vans. Companies now combine electric vehicles, delivery robots, parcel lockers, and priority customers. Optimizing all these elements together creates a complex routing and assignment problem, and that's exactly what we focus on this project. The original problem from the paper is extremely rich and complex. It includes routing electric vehicles, dispatching robots, assigning customers to lockers, handling prime versus non-prime customers, and even modeling battery levels and charging stations. While this makes the problem very realistic, it also makes it too large and complex for exact optimization methods like MILP to solve efficiently, especially for real-sized datasets. In fact, the paper itself relies heavily on meta-heuristics rather than exact solutions. To make the problem suitable for our course, we created a simplified version. We kept the most important decision layers, which is prime versus non-prime customers, EV routing using a classical CVRP formulation with MTZ constraints, robot service based on distance limits, and locker assignments with capacity and coverage constraints. At the same time, we removed battery modeling, charging stations, and time windows. This allowed us to focus on routing, assignment, and service mode decisions while still preserving the core complexity of a hybrid delivery system.
So I'll be going over the mathematical models that we use for our project. So first of all, here are a few of the parameters that we used. Examples are like the distance between nodes I and j, the demand for customers, the profit if a customer is served, the capacity of the EV, and the profit, etc. And similarly, the decision variables that we use for our projects where EV routing xij one if EV travels directly from node I to j, EV visitations, load propagation using MTZ constraints to avoid subtours, customer service mode, things like when will the customers get served and not, and robot assignment as well as locker assignments. So we assigned 1 if the lockers were served and 0 if they were not. For our model, the objective function was to minimize the total EV travel cost and robot travel cost while maximizing the profit collected from serving customers. At the same time, it includes a penalty if a non-prime customer is skipped. So the model must find the cheapest possible combination of EV routing, locker usage, and robot service while it still prioritizes prime customers. Now the constraints enforces the rules of hybrid systems. We have total of 9 constraints, which are flow conservations for EV and customers, MTZ capacity constraints so that EV load across the nodes and prevent subtours, customer service constraints, make sure each customer is served exactly one and prime customers must always be served. Robot service constraints ensures a robot can only serve a customer if the EV actually stops at the launch node, and robot must stay within their maximum range. We also limit the number of robots per EV stop, so we do not exceed the allowed capacity. Robot locker constraints ensures that lockers do not exceed their capacity and can only serve customers within their coverage radius. Together, these constraints create a realistic optimization model where EVs, robots, and lockers each play a role but must operate within their physical and operational limits. For our model validation, we first tested the MILP on a very small toy dataset with 5 customers, 1 locker, and a simplified distance matrix. The purpose here wasn't to optimize the performance, but to make sure the model logic was working correctly. The solution output showed on the slide demonstrates that each delivery node behaved exactly as we expected. The EV served 2 customers, the locker served 2 customers, and 1 customer was served by the robot launched from the EV stop. This confirmed that our code components, the binary service variables, flow constraints, capacity constraints, and objective calculation were all functioning properly. Running this toy example allowed us to verify that the model assigns customers only when they meet distance and capacity rules, and the EV route is valid with no subtours. Once this small test behaved correctly, we knew our foundation was sound and ready to be applied to the full 70 customers dataset. For our main experiment, we used the full dataset, which includes 70 customers and 20 EV vehicles. We evaluated different delivery strategies on a larger instance. We tested 4 approaches. The first is MLP model, which we solved with 330,000 second time limit. Even with that long time limit, the solver could not prove optimality, but it did return a strong feasible solution that we used as our benchmark. Then we tested 3 heuristic approaches, which was EV only. The second was EV plus lockers, and the third was EV plus robots. Each heuristic represent a different hybrid strategy, allowing us to compare how much locker and robots actually improve performance. And for all of this, we use the same distance metric, EV capacity, robot range, and locker coverage parameters. This ensures that any difference in performance comes from the method itself, not from variation in our data. Overall, this experiment setup gave us a fair comparison between exact optimization and heuristic solution, and it helped us understand how each delivery mode impact the costs of customer coverage.
Now I will go over the result for MILP. This slide summarizes the MILP performance for the full 70 customer instance. Using CBC, we obtained a very strong feasible solution with an objective of -2 to 7. The model serves roughly 68 customers, and we see that locker carry most of the workload, handling about 10 to 12 customers each, while robots are used only once. The EV component is very lean, producing just 2 short routes. We also ran the same model in Gurobi. Gurobi immediately reproduced a very similar lower bound structure around 2 to 7, -2 to 7, but it was not able to find a feasible integer solution close to that bound before hitting the time limit. The feasible solution Gurobi did return was much weaker, which highlights the complexity of this model at scale. So overall, CBC gave us high quality feasible baseline, while Gurobi confirmed how challenging the problem is by showing a large gap between the bound and feasible solution. This result established the benchmark of our heuristic that we will be compared against. On this slide, we compare the performance of our 3 heuristic approaches against the MILP benchmark. The EV-only heuristic performed the worst, achieving an objective of about 2 to 9 and serving only 14 customers. This shows how quickly EV routes become capacity limited when every customer must be visited directly. When we introduce lockers, performance improves dramatically. The EV plus locker heuristic serves around 45 customers directly and routes the rest to lockers, bringing the objective down to about 1 or 2, which becomes our best heuristic result. The EV plus robot heuristic performs better than EV only, serving 20 customers, but robots have limited reach, so the improvement is smaller. The overall pattern is clear. Lockers drive the biggest cost reduction, robots provide moderate benefit, and EV-only routing is not viable at this scale. These results set the stage for interpreting why hybrid system outperform traditional approaches. What this result really shows is why hybrid delivery system outperforms traditional EV-only routing. The clearest pattern is that lockers remove a large portion of the workload from the EV fleet. By serving many customers through lockers, the EV routes become shorter, less congested, and far more efficient. That's why EV plus locker heuristic is the strongest of the 3. Robot also help, but that effect is more localized. Their working radius limit how many customers they can realistically serve. So they mainly clean up small cluster rather than reshaping the overall routing structure. Comparing everything to MILP baseline reinforces this insight. The optimal model also relies heavily on lockers and use robot only when absolutely beneficial. Together, the exact and heuristic result illustrate how each delivery mode contributes to reducing cost and why hybrid system achieve better performance. To conclude, there are 3 main takeaways from this project. First, hybrid delivery combining EV, locker, and robot clearly outperforms any single mode strategy. Locker offer the largest efficiency gains, while robot provide targeted improvements for nearby customers. Second, by simplifying the original REVRP LPCP into solvable version, we were able to apply the optimization tool from this course. The MILP gave us a strong benchmark, and the heuristic showed how to scale the problem while still capturing the essence of hybrid system. Finally, this project reinforced core concept from our course, that is VRP modeling, capacity constraint, assignment structures, and the trade-off between exact and heuristic methods. Overall, we gain practical experience in translating a research model into an implementable engineering solution. Thank you.